this is the outline for today. The first 10 minutes will be covering an overview of what we have learned so far in terms of like the field generating electricity, the CO2 emissions. And then the second part we'll talk about thermodynamics. The first law, second law, various efficiency definitions. And then we'll go through the thermodynamics diagram together once for all, and hope we all know how to do draw the thermodynamic diagram by today. And the last part is the one fundamental efficiency you need to memorize from this class is the kernel efficiency. So if you say you are an energy expert but you don't know about the kernel efficiency, that would be not nice. So this is the overview. If you look at what we have learned so far is that we are asking you in provinces like, what's the energy content of certain field? And if you burn this 1 kilogram of food, how much CO2 will be released? And then we also ask you like, by burning this much of wood or coal, how much electricity can be generated, right? This is what I mean. Energy content in provinces 1, you know how to do this, and then find the emission factors. And then in this week's problem set, you are asked to find the emission factor of electricity. This metric is very useful when you discuss about electric vehicles, for example. In problem set 1, we asked you about, for the electric vehicles, whether it's cleaner to run it in California or in West Virginia, because West Virginia uses more coal to generate electricity, whereas in California, we do not use coal to generate electricity, and half of the electricity is generated from natural gas, which is much cleaner. And in the problem set 2, question 4, I guess you will have a sense of how clean this half natural gas is. Okay, so we already know everything from problem set 1, but then later the question comes: instead of finding the emission factors, how about we derive them by ourselves? That's why we learned combustion. We balance the equation, find out that by burning 1 kilogram of wood or coal, how much CO2 will be released. That's the previous job. Today, what we're concentrating on is the thermodynamics. That previously we were told that the coal-fired power plant is 33% efficient. That natural gas power plant is 45% efficiency. But where do you get that number? How do you get the number? That's what we are going to be focusing on today. Okay. So this is kind of a motivational slide. This is taken from the U.S. Energy Information Agency Administration, where all the official energy data are about the United States. This is the U.S. primary energy flow by sources and sector last year. On the left, there are various sources from like oil, natural gas, coal, renewables, and nuclear. On the right-hand side is on the different sectors, like transportation. As you can see, the majority of the fuel, 92% of the fuel for transportation comes from petroleum, oil, because we use gasoline and diesel. And then if you look at electric power generation, about 43%, almost half of the US electricity comes from coal sources. Okay, and from all these sources, many of them will need thermodynamics to calculate the efficiency. Thermodynamics is the basic tool you use to calculate the conversion efficiency from heat to generate electricity. That's what we are going to learn to review today. Okay, this is the quick quiz. This graph I showed you last week, it shows you the worst energy consumption by different energy sources, right? Coal, renewables, hydro, nuclear, natural gas, and oil. Can someone tell me which are those? Just now I talked about what is the thermodynamics, how the thermodynamics is used for, right? So among these different sources, which are those relevant for in terms of thermodynamic calculations? Anyone? Is the question clear? Yes.
Oil?
Yes, oil. Like, you know, for example, gasoline, right? We know the auto cycle from the car. Anyone else? Yes.
I mean, all of them involve thermodynamic processes, except for, I mean, they all technically do with hydroelectric, because you're gonna boil water, and that's not one of the, like, what are you referring to? Like, hydro would be the one that doesn't directly involve burning a fuel.
Right, hydro doesn't involve, so what I'm asking is that not hydro here.
Right.
Renewables such as photovoltaic, it does not directly relate to converting heat to electricity, so it doesn't involve. So in short, the answer here is that coal, we burn coal to generate electricity. I showed you earlier that 50%, almost 50% of US electricity is coal sources. And then these renewables, among them there are geothermal and solar thermal process. It involves heating up water into steam and use the steam to drive a turbine to generate electricity. And then also nuclear energy might be surprising to you, but actually nuclear power plant is very similar to a coal-fired power plant. They just use different sources of heat to heat up the water to generate electricity and use the electricity to run through a turbine, rotates the turbine to generate electricity. And then we talk about natural gas, right? Very clean source of electricity, and oil. That's a motivational slide. Then now we get into the basics of the thermodynamics. Let's take 1 minute to look at this problem. It's a problem taken from the lecture slides, but it highlights many definitions we need to cover today. The power plant, the fuel input is 1,000 megajoules, and the useful energy work, such as electricity, is 350 megajoules. The waste heat is 650 megajoules, and it's operating between two temperatures. The high temperature is 800 Kelvin, the low temperature is 300 Kelvin. Okay, so from here, these slides we're going to calculate the efficiency, thermal efficiency or first law efficiency, and also calculate the Carnot efficiency. And also another definition is effectiveness or second law efficiency. Okay, this is not on the. This is not in the handout. So before we talk about all those first law efficiency and second law efficiency, it might be a good idea for us to cover first law and second law first, right? So what first law basically talks about is the energy balance. The energy cannot be created, but it can be transferred or converted from one source to the other. So if you have one system with energy E, and then there is energy input and also energy output. The first law of thermodynamics tells you that energy input, the difference between energy input and output will be what is left over or what is taken away from the system, will be the change in the energy of the system. Typically, for the thermodynamic cycle we are going to talk about, the change of this system energy is zero. It's called steady state condition. Steady state condition. Basically, for steady state condition, what you care about is what comes in equals to what goes out. Okay. For example, in this diagram, what comes in is that 1,000 megajoules of fuel input. What comes out is that 350 megajoules of electricity plus that 650 megajoules of waste heat. As you can see, although it looks trivial here that 350 plus 650 equals to 1,000, but this is what we need to do, the energy balance. Sometimes not all the values are given, so you will need this first law to find out them. For example, if you are not given 350 megajoules here, you're only given 650 megajoules. If I ask you what will be the output for electricity, you will use this balance. You will use the first law to find out that our input is 1,000, the waste heat is 650, therefore the electricity is 350. That's the first law. And throughout the process, sometimes we'll write Q and W. There are just different notations for this energy. Q is referred to heat specifically, and W is referred to work, such as electricity. And then we talk about second law. Second law introduced the concept of entropy. Like the entropy of the system can never decrease. The whole system, the entropy can only increase or stay the same. When the entropy doesn't change, it's called isentropic. We will cover later. But one useful thing to memorize here is the second law relates Q equals to T, temperature, times difference in entropy. Okay, that is what you will need for the thermal cycle calculation. This is what we covered earlier. First law efficiency is also called thermal efficiency. It's just use useful heat work divided by your input, we give you 35%. And the kernel efficiency is what we will derive at the very end of this class. And the formula is like that. Does everyone has a handout? It's on the handout actually. So there is another definition which is called second law efficiency or effectiveness. It's the ratio between your thermal efficiency divided by the kernel efficiency. This matrix is mainly for like to evaluate how effective your power plant is. For example, if your effectiveness is 100%, you reach the kernel efficiency. That's the maximum efficiency you could ever get by operating between the two temperatures. So, for example, here, what we see is that the second law efficiency is about 56%. It seems that there is still plenty of room for further improvement in terms of engineering design, etc. Okay, everyone clear? Okay, so those are the basics of first law, second law, and different definitions of the efficiencies that you may be asked during exam, for your exam or problem test. Just now that problem is about the coal-fired power plant, and if you draw the thermal cycle for this power plant, it looks something like this. It's a little bit complicated. The reason it's complicated because you are boiling water. The water has phase change, therefore you have this diagram. Inside here, you have liquid and vapor coexisting. Here is liquid and here is vapor. You do not need to understand this. I'm just showing you how does a coal-fired power plant or the nuclear power plant looks like in terms of the thermal cycle. The working fluid, as I mentioned earlier, that coal and nuclear, they were used to use the heat to heat up this water into steam, and that steam will go through. Okay. That steam will go through this process, driving the turbines to generate electricity. So, there are many technical terms in the thermal cycle. It might be a good idea to know what they are referring to, because these are the ways we navigate these thermal diagrams. Can anyone tell me what does isentropic mean? Yes?
Reversal and adiabatic.
Oh, you are coming from the engineering background, right? Yes. In a simpler term, like for this class, what you need to know is that for these terms, they dictate how do you move in this thermodynamic diagram. Isentropic means the entropy doesn't change. Isothermal is a fancy term for constant temperature. For example, what I mean by it provides a direction is that in the lecture you might see some diagram in terms of pressure and volume, and also temperature and entropy, right? And you need to draw this diagram. For example, over there, that's a TS diagram here. You need to draw how does them flow. And all those terms give you the direction. For example, if it is isentropic, it means that the change in entropy is zero. Therefore, your states only move vertically on this diagram. If it is isothermal, the change in temperature equals to zero. You move horizontally in this diagram. Same thing applies here. For isobaric, it's called constant pressure. So you go this way. And if it is isovolumetric or constant volume, you go this way. And because when we describe a process, we normally tell you it's isentropic compression or isentropic expansion or isothermal heat addition, etc. Right? When we tell you it's isothermal, we are telling you that if you are here at 2, you are going to move left or right. Okay, so it's useful to kind of know what are they referring to. For example, isentropic and isobaric. This Otto cycle is simpler. It deals with air. It does not deal with water. So the typical application we can think about is a gasoline car for the Otto cycle. In the class, we'll draw this, right? For the Otto cycle, the process is that you have the piston and cylinder. The first process is that it compress the air to a smaller volume, and then ignite the air and fuel mixture over here in a constant volume process as 3. And then after you have this very hot and high pressure air mix there, it will drive the piston down to drive your wheels, etc., providing the work. And then that is this as you can see, the isentropic process from 3 to 4. And then we normally just connect 4 and 1, so it's a closed cycle. So that's it. That's for the Otto cycle. That how it works in a gasoline-powered car. What is interesting is that the Brayton cycle, it relates to natural gas. One reason that you need to care about this Brayton cycle, be familiar about this, is that you know about the fracking, right? The natural gas is leading a kind of energy revolution now in the United States. And United States now is like thinking of exporting some of the natural gas to Europe and to counterbalance the geopolitics between Europe and Russia. And natural gas may be the intermediate source of fossil fuel that will be seeing growing consumption over the next decade or so. So the way we use natural gas to generate electricity is this process where the fresh air comes into the compressor. You compress them isentropically from 1 to 2. You see, isentropy is just vertically, go this way. And then you inject fuel, natural gas, and you combust them. You have this very high pressure and temperature gas after this constant pressure process, 3. And then this high pressure and high temperature gas will go through a turbine, rotating the shafts, providing electricity.